So what we tried to do here, first off, I'd like to thank Dr. Jerry Spears for his guidance in this study, Dr. Helt for his support and guidance, and then, of course, Dr. Engel's leadership. This was done out at the Akron, Colorado, Eastern Colorado Research Center. They're in Northeast Colorado. And as we get started and talk about kind of, I guess you'd say the justification for why we were even curious about doing a study like this, I'm not going to spend a lot of time on this slide. This is basically just looking at some published studies where we've seen that, hey, the hydroxy trace minerals, particularly the IntelliBond product, has been evaluated relative to sulfate. The first two studies there on the left are relative to copper sulfate, and the far one on the right is a study where zinc retention was used to look at the relative bioavailability relative to zinc sulfate. We've established that already with a couple different introductory slides, but there is a difference in bioavailability, obviously, in the hydroxychloride sources versus the sulfate sources, particularly with copper in the face of antagonist in the diet. What I'd really like to focus on from an introductory standpoint and just kind of give you some perspective as to why we did what we did with this particular trial, study that was published in 2020, Jalali in Dr. Engel's lab, is basically a similar kind of study from a design standpoint to what we're going to look at today. It was a study that was done over 2 years, 2 production cycles. The treatments were fed in a free choice mineral supplement. The 2 treatments that we had in this particular trial would have been a supplement that was fed with 100% of the copper, zinc, and manganese coming from a hydroxychloride source. And then the other treatment would have been where 75% of the copper, zinc, and manganese came from sulfate and 25% from an organic source. So a combo treatment, if you will. And what you see is the response here that we noticed that stuck out to us was the pregnancy rate to AI. We improved it numerically at least about 6 percentage units. And that's kind of a common theme as you look through the literature, as you evaluate improved sources to sulfates. You'll see a pregnancy rate to AI oftentimes in that early part of the breeding season. And if you look to the far right of that slide, you'll see liver copper concentration and zinc copper concentration was improved after 1 and 2 years of supplementation with the hydroxychloride sources versus those combo treatments. So that was kind of a similar trial with regard to design, and we said, hey, look, we know there's a difference in RBV in these different sources. This is an actual production response that we saw in a similarly designed study. The other thing I'd like to show you, just kind of give you again some perspective as to what we did with this particular study. The study published by Stanton and others around the turn of the century is one that really provides some food for thought, we think. This is a study that looked at level and source. And the interesting thing about this, there's 3 treatments here. You have a low-level sulfate treatment where about 50% of the copper requirement was being met with copper sulfate. Then you had a high-level sulfate treatment where 100% of the NRC requirement was being met with sulfate, and then a high-level organic treatment that was intended to meet 100% of the NRC requirement. The trial was run from calving basically through weaning, so middle of March through into September. And what you see is that liver status, at least with regard to copper, was improved with the 2 higher levels of supplementation. Didn't matter if it was from sulfate or from the organic. Significantly so when we looked at it at breeding. But what's also interesting, if you look at the bottom of the slide here in this particular table, if you looked at pregnancy rate to artificial insemination, even though this high level of sulfate treatment resulted in an improvement in status, it did not result in an improvement in pregnancy rate to AI relative to the improved source. In fact, it was same as the low-level sulfate treatment. So the other thing that's not up here is that the high-level or inorganic or high-level sulfate treatment, those cows actually lost significantly more body weight relative to the other treatments in this trial as well. So the reason I bring this up is that it kind of begs the question, is feeding too much of a sulfate a good thing? And the reason that that's important is if you look in the industry now and what's typically done from an industry standard standpoint is a lot of times you'll see 2x, 3x NRC requirements being fed to range cattle. And I know why it's done, because it's a cheap source And it gets back to that CYA if you're a consulting nutritionist and trying to make sure that you don't have any deficiencies. But this kind of study kind of suggests, well, maybe you can have too much of something like a sulfate source in terms of actually having a production negative effect. So that's why the objective of this study was to determine the effects of copper, manganese, and zinc source and concentration in free choice mineral supplements. We looked at mineral status, reproduction, and performance of those cows and their offspring up through weaning in this particular data set. And we did that over 3 production cycles for this. So this is a 3-year summary of those production cycles. A trial again conducted over 3 years. It was started January of 21 and we'll go through December 23. 3 treatments. The first 2 treatments there are where we're trying to target the NASEM requirement for copper, zinc, and manganese, either with sulfate or with a hydroxychloride. And then the third treatment there is basically half that rate with a hydroxychloride. Okay? 180 Angus cross cows to start the trial. We're currently with 160 cows because one replicate dropped out. Cows were blocked by weight, body condition, age, gestation, and liver trace mineral status before they were randomly assigned a replicate, then assigned a treatment. Replication's unequal among the treatments because one of the replicates was discontinued from the trial. So as you look at the data, 3 pastures or 3 replications per year for the 1X sulfate treatment and the half-rate IntelliBond treatment. And then 2 pastures or 2 replications per year for the 1X IntelliBond treatment. 20 cows per pasture, so 20 cows per replicate. Replicate was considered the experimental unit, and pastures get rotated monthly to try to prevent pasture from becoming a confounding factor. Cows were synchronized and timed AI. 2 AI technicians randomly bred half of the cows each from each replicate across the treatments to try to make sure that was even. Then the cows would have been exposed to cleanup bulls for 46 days, so pretty short breeding season. Calvings during March and April, breedings typically July and August, weaning is that October time frame. Again, these mineral treatments would have been delivered to the cows via free choice mineral supplement. Again, trying to do it as real world as we can from an application standpoint later for producers. So mineral intake gets recorded monthly. Observations, body weight, condition score, and your pregnancy rates obviously are things of concern. Liver samples were collected on 10 cows per rep in the subsequent liver analysis, so about half the cows. And then birth date and weaning weight were collected on the calves. So here's your treatments and kind of the formulation of the mineral supplements to achieve what we're trying to do with the treatments. Before I get into that, we should say too that we're trying to achieve an 114 gram per head per day intake. That's about 4 ounces per head per day. The reason we chose that is that's kind of an industry standard in the United States in terms of what most commercial formulas are trying to do. What you see here is that basically, again, you have the 1X NASEM sulfate treatment, the 1X NASEM hydroxy treatment, where again, our target there is to get 100% of NASEM requirement met with either hydroxy or sulfate. And if you do a 4 ounce intake and you make some assumptions on cow forage intake per day, basically that mineral formula is 1,000 parts per million copper, 3,000 parts per million zinc, and 2,000 parts per million manganese. That third treatment or the half rate treatment, again, that's from hydroxy, and that would basically be half, right? So 500 copper, 1,500 zinc, and 1,000 manganese. So here's what actually happened with mineral supplement intake. We're shooting for about 114 grams per day, and you can see in year 1, which is the far left over here, they were nearly 2x that for much of that year. The red line at the bottom is kind of where our target is. So we made some adjustments with regard to feeder location relative to water and salt into the equation, et cetera. And we've gotten that intake down closer to target over years 2 and year 3. If you actually look at the average intake over the 3-year time frame, we're actually sitting probably closer to 1.5x NASEM for the 1X treatments and closer to 75% of NASEM for the half-X treatment, if that makes sense. But the good news is that third treatment is still half the rate of the other 2 treatments in terms of what we're trying to compare from a level standpoint. Chemical analysis of the grazed forage. I don't have year 3 up here, but year 1 and 2, you can see average forage samples tell us that our copper level is pretty low, our zinc level is below requirement. The other thing I have highlighted in red here is that the molybdenum level is certainly getting in that range where it can become a problem as an antagonist, certainly for copper. Oh, I didn't mention earlier too on the mineral formulations, they're 12% sulfur, and that was intentional. The water quality is really good out at Akron, so we basically are forcing a potential copper antagonist into those formulas with that 12% sulfur level in our mineral supplements, and that comes from elemental sulfur. Just so you know, we have 2 potential copper antagonists in the equation with that sulfur level and this moly level in the forage. So here's what happened with regard to body weight and body condition. A lot of numbers up here, but I'll save you some time. No differences, okay? No differences after year 1, 2, or 3. The cows actually did excellent. We had 1 year that was an extreme drought. We had another year that was above average normal, Terry, in terms of rainfall. So ranch managers did an excellent job with regard to protein and energy management on those cows, but really nothing here to see, no difference in body weight and body condition of the cows. Where we do start seeing some differences are in trace mineral status. This is copper status, and we use liver concentration as the parameter there just to set up this slide on the y-axis. We have your concentration on a dry matter basis, milligram per kilogram. Your initial, of course, is not supposed to be different, and it's not, but the cows actually started out in pretty good shape from a trace mineral or copper status standpoint. After 1 year of supplementation, all of the treatments improved, and there was no difference across treatment. But by the end of year 2 and by the end of year 3 of supplementation, we start to see the hydroxy treatments pull away from the sulfate treatments in terms of copper status. Even the half rate treatment is different than the sulfate treatment for copper status. This is zinc status, and you'll notice a lot of the same things. The slide's set up exactly the same way. Initial, of course, is not different. An improvement for all 3 treatments and no difference after year 1. Again, after year 2 and after year 3, we start to see the hydroxy treatments pull away from the sulfate treatments in terms of zinc status with regard to liver concentration. Here's what's really interesting. This is manganese status. Again, looking at liver concentration, no difference up front, no difference after year 1. But even with manganese liver concentration, after 2 and 3 years of supplementation, we're starting to see the hydroxy cows pull away from the sulfate cows, which is unusual, right, Dr. Spears? We just don't typically see manganese changes in status. Did that result in a production response that actually pays the producer? Here's your pregnancy rate to artificial insemination. Year 1 pregnancy rates to artificial insemination, no statistical difference, even though there's a little numerical increase here for the 1X hydroxy cows relative to sulfate cows. But you can see by year 2 and year 3, we start to really see a change and a benefit of using that hydroxy trace mineral relative to the sulfates and pregnancy rate to AI. Again, even the half rate relative to the sulfate. Because of this improvement in pregnancy rate to AI, you get more calves earlier in the calving season. That starts to domino. The last thing I'll show you here is actual weaning weights. You start to see those same trends. And this is what really pays today. Year 1, no difference. After year 2, a numerical difference there between the 1X and the sulfate. But even when we get out to year 3, we see both hydroxy treatments, both levels, with a more significantly heavier average weaning weight relative to the sulfate. So having said that, hydroxy copper, zinc, and manganese supplementation improved copper, zinc, and manganese status with regard to liver, pregnancy rate to AI, and actual weaning weights of calves compared to the sulfate sources of the copper, zinc, and manganese. Thank you.